Alright, today we would like to talk about how to make a line following robot using STM32. Here's today's agenda. We'll start with the tools and materials we need, then move on to the installation steps, model settings, and operation checks. After that, we'll explain the core line following algorithm, and finish with a few final notes. First, let's look at the required items. For hardware, we will need USB cable, STM32 board, DC motor, tires, sensors, the robot body. Once assembled, this will form the complete robot. For software, we will need Simulink embedded coder, MATLAB coder, Simulink coder, and the STM32 hardware support package. In short, we will use the MathWorks products with STM32 software. After preparing everything, we will check the sensors and motors are working properly. So with that, let's move on to the installation step. First, please open MATLAB and go to Add-ons. From there, click Get Hardware Support Package. Next, type Embedded Coder Support Package for STM that we mentioned earlier and click Install. After accepting the license agreement, select the appropriate board for our device and proceed to the next step as guided. We will then need to download files from external link. Make sure the version is correct. Unzip it, run the .exe file, and finally run the validation process to confirm that everything is set up correctly. After that, continue the installation of STM32 CubeMX following the same steps. Then proceed to install STM32 Cube Programmer as well. You can simply follow the instructions to complete the setup. Next, we will configure the configuration parameters from Model Settings. Open a blank Simulink model and go to Modeling, Model Settings. Under Hardware Implementation, select the hardware board to be used. For this project, choose the STM32 F3 series. Then, in Code Generation, set the toolchain to GNU tools for ARM embedded processors. Select the build configuration based on our purpose. Faster runs for sensors monitoring or operation checks while connected to the PC. Faster builds for standalone operation. Next, in connectivity, under Hardware Implementation, connect the PC and the robot via USB. Check the serial port number in Device Manager, COM5 in this example, and set it accordingly. After that, create the .ioc file for STM side software integration. Specify the project name and select the hardware board. Click Launch to open the generated project. From here, proceed with the pin configuration. This is the STM32 board used in this project, based on its circuit diagram and the corresponding pin assignment table. We will configure each pin in CubeMX. For example, assign ADC to PA4, PA5, and GPIO timer to PA10 and PA11. Start by selecting the required functions in the pin configuration view. Since we are using the ADC, go to Analog, ADC, set it to single-ended, and enable DMA request add. Then in parameter settings, change end of conversion to end of sequence of conversion. Because we are handling two input signals, set number of conversion to 2 and confirm that channel 1 and channel 2 are assigned. Next, adjust the clock configuration as needed. And in Project Manager, ensure that Do Not Generate the Main is checked. In Advanced Settings, confirm that low-level driver is selected and that all visibility checkboxes at the bottom are cleared. After saving the project, the CubeMX sensor configuration is complete. Then proceed with the Simulink setup. Open the library browser and navigate to Embedded Coder Support Package for STM. Select our board and choose the analog to digital converter block. Set the ADC module to 2, following the earlier pin table, and set the number of conversion to 2. Since the two ADC signals are output on a single line, add a Dmax block to split the signal into 2 separate lines. Once all settings are complete, go to the Hardware tab and run Monitor and Tune to verify the sensor signals and detect correctly. With the sensor configuration completed, we will now verify motor operation. First, configure the pins in CubeMX as before. Assign timer 1 channel 4 to PB11 and GPIO output to P810. After assigning the pins, open the Timers tab, select timer 1 and set channel 4 to PWM generation channel 4. Next, go to Project Manager, Advanced Setting, switch the driver to LL, and clear all visibility checkbox. Save the project to apply these settings. In Simulink, use the digital port right block to control the motor rotation direction, and the PWM output block to set the motor output. From the library browser, place both blocks onto the canvas and add a constant block. Set the rotation direction to 1. This time it's going to be counterclockwise, and the output value to 50. Then configure the digital port right block with the appropriate port name and pin number, and set the timer module and enable channel for the PWM output block. Finally, run Monitor and Tune to confirm that the motor operates correctly. Since the initial operation check is complete, I will now explain the line following algorithm. The robot has left and right sensors. The right sensor shows a low value when it is on the black line, and the left sensor shows a high value when it is on the white surface. To stay on the black line, we drive the left motor and stop the right motor when left minus right is bigger than 0. In Simulink, this logic is represented as follows, and we build the model to control both motors. Because we will deploy without a cable, this time we set code generation to faster build. After that, running build, deploy, and start will enable the robot to perform line following behavior. This is a free demo designed for those who do not have access to actual hardware, allowing us to experience a line following robot through simulation. The demo includes models for hardware implementation using the training tracer, making it suitable for MBD education as well. We encourage you to try it out. Thank you very much for watching the video. We hope you enjoy it.